photochemical processes in atmosphere stopped and when oxygen appeared in atmosphere. So in a very simplistic way, how we can use it. And so what this is a measure of deviation from this terrestrial fractionation line, from this linear relationship. So basically, when we don't see deviation, when this deviation is 0, it feeds on this predicted line. And when deviation is large, like here, it means that it's off this line. And so if we start going from the past, from Archean times, we see this large deviation until we get to 2.5, 2.3, and then everything collapsed on terrestrial fractionation line. So that was a major evidence that sometime around here was a great oxidation event, oxidation of atmosphere. So when I came to this game kind of in 2001, I had experience working already on this Paleoproterozoic succession, so I was familiar with stratigraphy of the series. I worked on carbon isotope chemostratigraphy, and so my interest was, can I sort of focus on this transition, and can I constrain when exactly it happened? And so to address it, sort of after our study of Deutschland formation that I just showed with this positive carbonates, we went to next unit to where we see this very organic rich shales, Tangle Hill and Rundhoek. And the reason sort of we went there, and again, don't worry about all these names, because we were able to get rhenium osmium H for this unit. It's 2.316, and we saw beautiful pyrites in this unit that we can see lamination bending around these pyrites. We could see that they formed during early diagenesis before the compaction, and then we can potentially constrain conditions in atmosphere at that time. So here's this pyrites in thin section. You can see that lamina kind of bending around them. You can see the radial growth. You can see sort of central core different. You can see this stuff that we interpret as a potentially microbial meds that were sulfidized, but that's open to interpretation. And here's potentially repubs of this microbial meds. So we did sulfur isotope work, and I should mention that it's not like we were first who got interested in these units. Ian Cameron before did sulfur isotope work and found this very negative sulfur isotope values, which in traditional view would be interpreted as an increase in sulfate level in surface environments. But we were first to do multiple sulfur isotopes, which showed that basically sulfides were sitting right on this terrestrial fractionation line, and there is no evidence for photochemical processes in atmosphere at that time. So with this H at 2.316 that we established with rhenium osmium dating, and with this multiple sulfur isotope data, we were able to put a point on a time scale that at 2.32 was already enough oxygen in atmosphere to stop photochemical processes. And here's this H that was obtained by Colorado group, Judy Kahn and Holstein. And there are other interesting things about this initial osmium ratio that very low, but it's for sake of time, I will not going to talk about it. Okay, so but rhenium osmium H's are model H's, and potentially they could be wrong. And so with this, I kind of always had in my mind, what if our H was not correct? And Birger Rasmussen, with his sort of expertise in petrography combined with geochronology was able to test it. And so I sent him these samples, which I didn't expect to be tufts. I expect, because he also worked on xenotime, which grows like in thin, sandy, silty beds in shales. And so phosphorus from shale, if it migrates into the sandy, porous beds, it can produce xenotime crystals during early diagenesis or during fluid migration. So I basically selected for him samples with thin, sandy, silty beds in a shale. And when he looked on them, he reinterpreted them as a tuff beds. And the reason is because in these samples, glass shards has been replaced with pyrite and preserved as these intricate forms of sulfites. And also he saw these zircons sitting in this fine grain, and you can see like how thin this tuff beds. So that's not something you kind of collect comfortably before lunch and when you feel satisfied that you got the age. It would require maybe several months of your work. But with this type of material, with modern technology, you can now drill out plug of this zircon out of thin section, mount it on a sort of shrimp mount, and take it to shrimp and to date it. And what he can get out of it is the age that we keep coming again and again. We just talked about it in North America, and so exactly the same age in South Africa. So basically, we can kind of walk on the same ash bed, on the same tuff from Canada to South Africa, and we can link this stratigraphy above and below this tuff bed between two continents. And here's one, so he found several of these layers, and some of them work better than others. And obviously, if you have this thin tuff bed, you have some inherited zircons, older zircons. You might get some that were produced during metamorphism. So it's a complicated process, and but the interesting thing that it's possible to date it. And so to summarize for this part, what we this age confirmed rhenium osmium age for this unit, and confirmed that at 2.32 was oxygen in atmosphere. So with this in mind, we kind of decided, what if we go down? So we just established that was oxygen here in this unit time bottle. What if we drop down back to this unit that where I did my part of my PhD? So it brought us back to Deutschland Formation, and in Deutschland Formation, what we found was very interesting. Again, I just showed you this carbonate values in low part negative, positive in upper part. For sulfur isotopes, we found mass-independent fractionation in low part and lack of mass-independent fractionation in upper part. So in this unit, we basically have been able to catch the rise of atmospheric oxygen as close as potentially we ever will be able to do. There is a sequence boundary here, and there is a time and thickness that not characterized. So we are not exactly standing on a touching with our finger this transition in oxygen, but at least we are getting relatively close to it. And that pushes down to all the kind of undated part of the sequence. So all we know here that here is 2.32, here is 2.48, and we are somewhere between, and at present there is no age for this unit. And if we go into this unit, we find these lenses with oolites, and these oolites already have this sort of iron coating on them, suggesting some oxygen appearance in atmosphere and shallow marine environments at that time. Okay, so I don't expect you to get much out of this figure because it's too complicated, but sort of it's just to show how we process, how we work on this. So we go to different basins worldwide, we collect chemostratigraphical data, we collect sedimentological stratigraphical data, we do geochronology if we can, and idea is out of this complex sort of stratigraphical framework, but based on generation of geologists working together to reach into something that we can bring to sort of general public and explain it on with a simple time axis at the basis and showing various events. And so here's 3 or 4 glacial events shown in these blue lines. In green here is evidence for reducing conditions, in red evidence for oxidizing conditions. Here's various indicators that arranged in terms of atmosphere and ocean. But basically what is striking here, that we see this transition from reducing conditions to oxidizing conditions between 2.5 and 2.2 billion years. And we can see that in association with this transition there are these 4 glacial events, and in association with this transition is this change from stable carbon cycle to very sort of irregular and kind of bumpy carbon cycle, and back eventually to stable carbon cycle, but similar to Phanerozoic. Okay, so that brings us back to this longer-term curve, and we can ask several questions. So basically, this I just try to introduce you to geological record. That's what we have in our background when we are kind of trying to do modeling or thinking about Earth system evolution. And so we can ask several questions about this record. So what factors were responsible for this largest and longest carbon isotope perturbation in Earth history? Like, what is responsible for this 150 million years of this extremely positive carbon isotope values? Why this Lamagundi excursion ended? Like something lasted 150 years happily, and when that disappeared, like, why did it happen? How much of oxygen, how much of partial pressure of oxygen changed during and in the aftermath of Lamagundi carbon isotope excursion? So like basically how high oxygen went here during the Lamagundi excursion and what happened to it after. And just a note to get you oriented, but amount of oxygen that would be produced during this event based on a burial of organic carbon would be incredible. It would be between 12 and 22 times present atmospheric level. So based on simple carbon mass balance kind of modeling. I mean, people might challenge this carbon mass balance modeling. There are ways how obviously it can be interpreted in different ways. But that's a message that you would get from simple carbon mass balance modeling. And then you can say, well, some of it obviously was used to oxidize crust, to oxidize iron in crust, to oxidize sulfur in crust. Some of it was used to oxidize reducing compound in hydrothermal flux in ocean, but like how much of it actually stayed in atmosphere, remained in atmosphere unused. And you kind of think that it could have been quite a lot. And so the question is, can we balance it? Can we balance this sink for oxygen at that time and fluxes of oxygen. And so that's the second part of my talk. So if you got tired of geology, we now switch to geochemistry. So what we will do, a simple bookkeeping exercise on where this oxygen went. And it's simple because I'm not really a high-level modeler, but also it's simple because the level of details we have is not very high. And so we kind of, there is no point to develop complicated models if variables are still very poorly constrained. But basically, a redox state of atmosphere and ocean controlled obviously by oxygen content, but also it's controlled by what happened to carbon, sulfur, and iron in a crust and atmosphere, ocean atmosphere. So basically, carbon, when it's buried as an organic carbon in the sediments, it means that equivalent amount of oxygen is released to atmosphere. If carbon is exposed, like if you cut the wood, piece of wood, and burn it in your fireplace, or leave it outside of your house and let it slowly get rotten up, it will use up exactly the same equivalent of oxygen that was released during growth of this tree. So basically, here's the story that if you want oxygen to increase in atmosphere, you have to take this tree and to bury it in the sediments and not let it get rotten. So the point is that carbon, when it's buried in the sediments, removed from system, lead to increase of oxygen atmosphere. When it's remineralized, it consumes oxygen. The same with sulfur. When sulfur gets converted into sulfate and buried as a sulfate evaporite, it used up oxygen from atmosphere. When sulfur is buried as a pyrite, it releases equivalent amount of oxygen into atmosphere. The same with iron. If iron buried as an iron 3+, it's consumed oxygen from atmosphere. If it's iron 2+ buried, then it's not. And why do we care about this redox state of atmosphere and ocean? Because I will show you that it has implication for content of nutrients and micronutrients in the ocean. So it can, by itself, feed back to the productivity in the ocean. Okay, so the way so now how do we constrain, like how much of oxygen went to oxidize iron in a crust? It's difficult to do, right? So one way to deal with it is to see how composition of shales change for a time. So shales is why do we worry about shales? Except that there is a large group of people that here that worried about for their life. But the reason we worry about shales because shales, in terms of iron, they have a very high iron content, 6–8% of iron. So they are a major sink for iron that comes out of continents. Shales are fine-grained rocks, so they are more likely to react with atmosphere and ocean. Whereas if you take sandstone, like basically you broke a piece and you transported it and dropped in an environment and nothing happened to it. So shale or clay minerals are more likely to record this interaction with surface conditions. And shales are very abundant. They are common sedimentary rock. And so they play a major role in iron cycle as far as what oxidized on the continents and delivered in the rocks. Like carbonates have very little iron, sandstones have 3 or 4 times less iron, conglomerates has normally almost no iron. So that's why we're worried about shales. So what we decided to do, something simple, like in early days when people used to do wet chemistry, they used to collect this data on iron-3 and iron-2 content in shales. Like with development of new technique, it become kind of unpopular, and in last 10, 20 years, you hardly can find any data. But there is this huge amount of data available in literature from early days when people used to spend money on it. And so what if you plot shales with age older than 2.3? And why I selected older than 2.3? Because it's approximately when oxygen increased in atmosphere. So obviously, when you start talking about world record, it's not simple to put where rise of atmospheric oxygen happened on the continent where you've never been before, right? So, but through chemostratigraphy and geochronology and correlations, I can approximately do it. And so here I put shales that I think older than the rise of atmospheric oxygen. And what is interesting here is that they all have more iron 2+. So most of iron in these shales is present in reduced state. So here, what else is shown? Various continents in different symbols. Here's average for shales before the rise of atmospheric oxygen. Here's the composition of the mantle. So you can see that it's basically it's not more oxidized or not more reduced than the mantle. And that will come to play a little bit later. Here's the rise of atmospheric oxygen. Here's a transition to oxygenated environment. I put 2.1 here because it's the time when Lamagundi excursion ended. So when release of oxygen potentially ended to atmosphere, and when kind of carbon isotopes went down to 0 values. So what do we see here? We see similar record here to Archean, but suddenly we get all this stuff going on. So what happened? Like iron in shales responded right away to this oxidation of the atmosphere with oxidized iron appearing in the shales. Okay, so here's average in yellow, and we are significantly more oxidized compared to mantle. Here's the next interval after the rise of atmospheric oxygen, sort of this time when people call it sort of boring billion years. Things get messy, but it's expected. So we see a lot of reduced shales, a lot of oxidized shales. And what all we can do here is just to take average. And you can say, well, how representative this average? Well, you know, that's the best we can do for this. So let's just play with it and see where it gets us. Okay, so here's a summary. So here's just average values for each of this time interval. And here's a quite interesting record. So let me see if I can track it down. So here's Archean, average shale. So it sits on the same line as mantle. So it's not more oxidized or reduced than mantle. Here's rise of atmospheric oxygen. It jumped right here. So it's more oxidized, and note that it has less total iron. So basically, if we approach in this end, we have less iron. Next interval, after the rise of atmospheric oxygen, it jumped to less oxidized state and higher content of iron. And next one is Protérozoïque, and it's based on literature data from Russian sort of source. It jumped here, and Phanerozoic it jumped even here. So what does it tell us? Why? Well, we would expect that would be change in oxidation state of iron, but why is this change in total iron content? Well, the reason is that in an oxyc ocean, you transport iron from hydrothermal source and you add it to the shales. You also release it under anoxic conditions during diagenesis from sediments and added to the shales. So as a result of it, shales will be enriched in iron. Under oxic conditions, you cut off this hydrothermal flux of iron, and you cut off this benthic iron flux coming back to the water column. So that's all consistent. It's nice. And what we will do with it is something very simple. We ask, like, how much oxygen would we use during the time of this great oxidation event to take a shale out of this average position to this average position. So basically we want to know, like, how much oxygen we can donate to shales to get them more oxidized, so we can remove this oxygen out of atmosphere and not worrying about too much oxygen in atmosphere. And so we will do this, or I do this simple math. I will not bother you with calculations, but where else can we put oxygen? Well, in our place, I mentioned sulfur. So what if we go into Archean sediments, in what form we find sulfur? Sulfur where is normally as a pyrite. So it's like you don't find sulfate evaporites in Archean sediments. Like you find barytes, and some people argued that some of it could be evaporites, except that we find it in deep water hydrothermal system, which is not a place for evaporite to be. As I showed to you and shown here, here's sediments deposited during the Slomagoundi event, and they all have indication of sulfide evaporites formed at that time. So now this is quite complicated, like how much oxygen we put into this sink. And we simply said, okay, let's just take a number and let's put half of the sulfur into pyrite and half of it into sulfite evaporites. And we calculate simple just how much oxygen would go to put half of the sulfur recycled from the crust into evaporites. And so here's a simple table, and it's certainly not necessarily representative of reality. It's somewhere close to reality. But the point here, we calculate oxygen source from carbon isotope balance, and we calculate oxygen sink using crustal iron recycled into sediments, crustal sulfur recycled to sediments, and volcanic source of hydrogen. And oxygen gains positive, losses negative, and so what we calculate here. Okay, so I don't want to bother you too much with numbers, but I want to emphasize one thing. What came very interesting from this sort of exercise, what will happen with organic carbon in Archean? So like in modern environment, if you recycle sediments and we have organic carbon get oxidized. But if you have an anoxic atmosphere, this organic carbon will not get oxidized. So basically you will take this old carbon and you dump it back into the sediments and bury it there. So if you include it in carbon isotope